Hello, thank you for joining me today. Let us go over the first question of this problem set MA166 Spring 2022 Exam 2. It says, evaluate the integral from 0 to 1 over 3 of x times e to the 3x dx. In this case, we can see right off the bat that our function here is just the product of two separate functions. One is a power function whose nth derivative can equal 0, and one is a different type of function. It might be exponential, sine of x, cosine of x, log of x, something like that, whose derivative will never equal 0, right? So in this case, there's pretty much one obvious solution here, and that would be integration by parts. Let's go ahead and do that. The integration by parts, as a reminder, says that if you have a function here, the integral of u dv, that can be expressed as uv minus the integral of v du. And this pretty much just extends from the product rule. If you reminder, the product rule is just dx of f of x g of x, that would be equal to f prime of x g of x plus f of x g prime of x. And you can kind of see the parallels here. You have f of x g of x here, you have f prime of x g of x here, you have this here. If you integrate both sides, you get f of x g of x minus f prime of x g of x, and that integrated dx would in fact equal the integral of f of x g prime of x dx. And you can pretty much see the integration by parts formula start to form out. So what's our next step in this process then? Our next step in this process is to obviously use the integration by parts method. That is to say that we need to select one function u and one function dv. Our u function is typically a function whose nth derivative can equal 0, because that way we can reach a state of an integral where it is just one function and not a product of two. So our u function will be x. So u here will equal x, which means that our dv function here will equal e to the 3x multiplied by dx. So you take the derivative of this, u equals x, du dx is equal to 1, and then you integrate this. And then you get v is equal to 1/3 e to the 3x, no differential dx. So now we can start setting up our new step, which would be uv minus the integral of v du, and that would be equal to x times 1/3 e to the 3x minus the integral of 1/3 e to the 3x, and then du in this case is just equal to dx, so we directly sub in dx in this case. We get that, and I'm leaving out the bounds right now. Actually, I wanted to mention that I'm leaving out the bounds right now. We'll incorporate the bounds later, but I want to save space and I don't want to clutter things too much necessarily. So I'll leave the bounds out for now, and then I'll put them in back later. So we have is equal to x over 3 e to the 3x, and then minus the integral of this is very simple. This just becomes 1 over 9 e to the 3x, and this is where we will put in our final bounds, our difference function. We have 1/3 at the top and 0 at the bottom. This in red, this will be in blue. So let's see, that'd be 1 over 9th e to the 1 minus 1 over 9th e to the 1. Oh my gosh, sorry. In red, and then minus in blue 0 e to the 0 minus 1/9 e to the 0, and this side cancels, that becomes 0. This obviously goes to 0. All we're left with is this last term here. We have a negative in here, we bring this out, this becomes a positive, so our answer is positive 1/9. That would be answer B. Hello everybody, thank you for joining me today. I hope you're having a good day as you watch this video. Let us go over question 2 of this problem set. evaluate the integral from 0 to pi of x squared cosine of x dx. Right off the bat, we can actually see what integration formula we need to use. In this case, we have the product of two different functions as our function, x squared and cosine of x. Now, when you have any two functions, you should immediately be thinking, I need to integrate this by parts. Let me remind you of how to do integration by parts. Let's say that you have two functions here. You want to integrate the product of two functions. We'll call one function v, and the other one is du. I'll actually have to flip the variables around. U dv, that would actually be equal to the product of u multiplied by the integral of dv, which is v, and then minus the integral of v du. And as a review, this extends from the product rule. Let's say you take the derivative of some product of two functions. That, of course, would be equal to f prime of x times g of x plus f of x multiplied by g prime of x. Now, if you were to integrate both sides with respect to dx, what happens then? This just becomes f of x times g of x. This becomes the integral of f of x times g of x dx, and then plus the integral of f of x multiplied by g prime of x dx. And then to solve for the integral of one of these things, you simply move the other one over, and then you achieve the same form as the integration by parts formula seen here. With that being said, let us start solving this problem using the integration by parts method. What do we need to do first? The first thing that we need to do is we need to identify which function is our u and which function is our dv. Now, in the case that we're fortunate enough to be blessed with a power function such as x squared, we want to make that always our u function, because we always say the derivative of u, since we're flipping since in our formula we're technically flipping the integral around from v du to u dv. And so, from u dv to v du, right? So the reason why you always want to do the power function is because with the power function, there exists an nth derivative such that the function just becomes 0, right? And when you have 0 or you have a constant value, then you're technically not incorporating a second function. You're just incorporating a constant value at that point. And then the integral becomes much easier to solve. Whereas if you did it with cosine of x instead, you will never reach a state where the nth derivative is equal to 0, because it goes from cosine of x to negative sine of x, then to negative cosine of x to sine of x, and then it repeats over and over again. And so your integral will be infinitely harder, because you keep integrating x squared, but you're not losing out that second term. So with that being said, we're going to set this equal to u is equal to x squared, take the derivative of both sides, du dx is equal to 2x, and then we need to set du on its own. Du is equal to 2x multiplied by dx, and then cosine of x, in this case, would be our dv. So dv is equal to cosine of x. Don't forget to include the dx at the very end. Now what you do with dv is you integrate that. So v is equal to negative sine, not negative sine, sine of x, and then you're done. So that's the first step. Now we reutilize the formula. U dv integral is equal to uv minus the integral of v du. In this case, this would become x squared multiplied by sine of x, and then minus the integral of cosine of x, and then multiplied by 2x dx. So now our integration by parts happens one more time. In this case, of course, our u function becomes 2x, so our du dx becomes 2. Our cosine of x becomes dv, dv equals cosine of x dx, and then v would be equal to, No, I'm so sorry. Not cosine of x. It would be sine of x in this case. Sine of x, and let me change that here. Sine of x, and that would be negative cosine of x here. And so integration by parts happens one more time. As in the first problem, I'm leaving out the bounds, and I'll reincorporate them later, just so I can save space and save writing time. So this becomes x squared sine of x minus, and what does this become? This becomes its own uv minus integral of v du. So that becomes 2x negative cosine of x, and then minus, in parentheses, that would be negative cosine of x multiplied by 2 dx, bracket closed. Okay? And as you can see, in this case, we have reached a state where the x from the x squared is completely eliminated and replaced by a 2 instead. So this out here becomes a positive. This becomes you can pull that negative sign out. And then this becomes a very simple integral. So this is x squared sine of x plus 2x cosine of x, and then minus, because we're bringing this minus sign to this plus sign, minus 2 sine of x, and then all of that between 0 and pi. I'll do all these calculations in red and all these calculations in blue. That would become pi squared sine of pi plus 2 pi cosine of pi minus 2 sine of pi, and then that'd be minus 0 squared sine of 0 plus 2 0 sine cosine of 0 minus 2 sine of 0. As you can probably already notice, all the terms with sine in it die off. So this becomes 0, that becomes 0, that becomes 0, that becomes 0, and this becomes 0 too, since 0 times anything is 0. The reason why it dies off is because sine of pi is equal to 0 on the unit circle, sine of 0 is also equal to 0 on the unit circle, and all we're left with is this. 2 pi multiplied by cosine of pi. As we know, cosine of pi is equal to negative 1. That would become negative 2 pi. Is that an answer to this problem? Yes. That's answer C. Hello everybody, welcome and welcome back. Thank you for joining me today. I hope you're having a good day as you watch this explanation video to question 3. Let's jump right into it. Compute the following integral. The square root of sine of x multiplied by cosine cubed of x dx. Alright, this looks like a very challenging integral, and this actually took me a very long time to solve. For a multitude of reasons. Not because it's like that difficult. Granted, it is pretty difficult. But anyway, I'm kind of tired, as you may tell. What we can do here is we can always try to extract a cosine squared of x, or in any other integral containing a sine cubed of x or something, try to split that up into sine of x and then multiply by sine squared of x. What this allows us to do instead is this allows us to be like, okay, well the integral turns into the square root of sine of x, and then multiplied by, what is this? Cosine of x multiplied by cosine squared of x dx. I honestly just try things here if you're not sure what to do. In this case, I tried out doing subbing this in for 1 minus sine squared of x. As you may know, the trig identity cosine squared x plus sine squared x is equal to 1. And then when you move over sine squared of x, you get that cosine squared of x is equal to 1 minus sine squared of x. That's how I made the substitution here. Let's do that. So now we distribute. This becomes negative square root of sine of x multiplied by cosine of x. And then minus the square root of sine of x multiplied by cosine of x multiplied by sine squared of x, all of that dx. And we can split this up into two integrals. This becomes the square root of sine of x cosine of x dx minus integral of sine 2 plus 1/2 is 5/2. The way that I did that is with this, you can consider this to just be sine of 1/2 of x still. And when you multiply exponents together, you just pretty much add the exponents. So in this case, 2 becomes 4/2, and then 1/2 added to that, that's 5/2. So it's sine of 5/2x times cosine of x dx. And then our integral emerges. We have two cases of u substitution here. So we can define our u to be the sine of x here and the sine of x here. And the reason we do that is because these sines of x's are actually the ones being operated on by a secondary operation, that notably being the two exponents in the corner. Now, if it were to be that the cosine of x's in this case were the ones under, the square roots, or they were under this 5/2 exponents, then in that case, we would consider our u function to be the cosine of x's. But as you can see, since they don't have anything attached to them, they are probably the derivative following the chain rule of the sines here. So let's do that. U in this one would be sine of x. In fact, u in this one also be sine of x. Du dx is equal to cosine of x. Same for here, actually. As I'm doing this problem, I realize that I don't actually need to split up the integral, but I do it anyway because it makes it simpler for me to follow. And then this becomes, that becomes du, sorry, not du. Now we need to sub dx back in here for whatever is equal to. In this case, it would become dx over du is equal to 1 over cosine of x, and dx would be equal to du over cosine of x. And now we have dx alone and on the numerator, which means if we can sub it directly back in, this integral becomes the integral of the square root of u multiplied by cosine of x multiplied by du over cosine of x. X's cancel, we're left with a u on its own, and the same thing applies to here. So I'm not going to write out that process again, but if you do the u sub for this one too, it becomes u to the 5/2 x, u to the 5/2 du, and this is just two different power functions, so we can easily use the power rule here for the integration. This would become, this is u to the 1/2. That would become 2/3 multiplied by u 3/2 minus 7/2. 2/7 u to the 7/2. But we use sub back in u for sine of x. So 2/3 sine 3/2 of x minus 2/7 sine of 7/2 x. And that would be your final solution. Is that a possibility here? Oh, and then of course, plus your constant of integration. That's Carlos at the very end. Say hi to Carlos for me, please. That answer here would be answer E. Welcome and welcome back. Thank you for joining me today. I hope you're having a good day as you watch this video. Let's go over question 4. Compute the following integral. The integral of innocent looking cosine to the 4th of x dx. And it is pretty innocent. As you may have seen if you come from the third explanation video, you can take any of these cosines of, or sines of a high power of x, and just try to continually split it up into pieces of cosine of x, or sine squared of x, or cosine squared of x in this case, but the point still applies. So in this case, we can split it up into two products, or product of two cosine squareds of x, which we see below, dx. And this is where we use the power function, or the power reduction function. I'll remind you, the power reduction function, I'll just memorize this formula. Cosine squared of x is also equal to 1 plus cosine 2 of x over 2, and sine squared of x is equal to 1 minus cosine 2 of x over 2. Okay, in this case we have two instances of cosine squared of x, so we would use the plus. 1 plus cosine 2 of x over 2, multiplied by that again. Okay, now I'm going to pull out a 1/2 from each of these so that our integral becomes a little simpler. If I pull out a 1/2 from each, that would become 1/2 multiplied by 1/2 on the very end. That'd be 1/4. 1 plus cosine squared of x, or cosine of 2x, multiplied by 1 plus cosine of 2x yet again, dx. Now we simply distribute. 1/4 multiplied by 1 plus 2 cosine of 2x plus cosine squared of 2x dx. And annoyingly, we have to do the power reduction formula yet again. 2x dx. My apologies. That would become 1/4. 1 plus 2 cosine 2x plus 1 plus cosine 4 of x over 2 dx. And then this would become 1/4, 3/2. I pull out a 1/2 from here and I put it back into here, plus 2 cosine of 2x plus cosine of 4x over 2 dx. And this just becomes a simple integration problem. That would become 3 over 8x. What's this? Sine 2 of x. So that'd be plus sine of 2x over 4. And then this would become 1. Okay, so that'd become, you pull out the 1/4 in the front. So it's 1/4 here. 8/32. 1 over 32 multiplied by sine 4x and then plus c at the very end. Is that a solution here? That would in fact be, and that would be solution D. Now if you're going to stick around a little bit later for the video, the reason why I was able to do 1 over 32 is because integral of cosine of cx, I'll write that out here, cosine cx, not cx, cx becomes equal to 1 over c cosine of 1 over c multiplied by sine of cx. And so you have 1/4 over 2, that's 1/8, and then multiplied by 1/4 out here. That would be 1 over 32. That is how I got 1 over 32, and that's how I did all the other coefficients of this problem, which results in an answer choice D. Hello everybody. Thank you for joining me today as we go over question 5. Before I begin though, I'd like to share with you guys a very funny story that has just happened to me 5 minutes ago. So I actually just recorded problems 5, 6, and 7 and their solutions, 6, 7. But the issue being, I forgot that I turned my microphone off earlier in the day, and I never bothered to turn it back on. So all my hard work at my 6 takes trying to get all of the explanations correct have just been wasted for no reason. So now we are back to square one with question 5. Let us compute this integral shown below, the integral of tangent squared of x times secant to the 4th x dx. So the first thing that we must notice right off the bat is that we have an exponent greater than 2 here. And that's a pretty big no-no when it comes to evaluating integrals. The reason for that is because most of our identities, sine squared of x plus cosine squared of x is equal to 1, or tangent squared of x plus 1 is equal to secant squared of x, and then vice versa. As you may notice, none of their exponents are greater than 2. So we need to find a way to split this secant to the 4th up into a product of terms of secant that have exponents of less than or equal to 2. Let us do that. Right off the bat, we can say, okay, I split this up into tan squared of x multiplied by secant squared of x multiplied by secant squared of x dx. But let's be careful here. We will need to use this trigonometric identity or a variation of it to solve this integral. But we only want to apply that to one of these two secant squared of x's. Why is that? Well, if we have the case where we have a tangent of x and a secant squared of x, there is a pretty good chance that we can use a u sub in this formula. If that's possible, we don't want to get rid of all of our secant squareds, only just as many as we need to. Let us continue by subbing in this formula here, this identity that is looks more like ta than tan. Tangent squared of x multiplied by tangent squared of x plus 1 multiplied by secant squared of x dx. This becomes the integral of tangent to the fourth x secant squared of x plus tangent squared of x plus secant squared of x dx. As you can see, u substitutions emerge. In both cases, u would be equal to tan of x, and then du dx would be equal to secant squared of x. We want to isolate dx on its own, because that's what we're going to sub back into this integral. So this would become dx is equal to du over secant squared of x. How did I get to this part? Well, you can effectively flip this upside down by raising it to the -1 power. That becomes dx du b is equal to 1 over secant squared of x. Then from there you bring du up into the other side of the equation, and that's how you get du over secant squared of x. With that being said, now we can pretty much start plugging in our wonderful functions here. So we have tan, oh my gosh, nice pen. U fourth multiplied by secant squared of x plus u squared multiplied by secant squared of x, and then multiplied by du over secant squared of x. Now in this case, I'm going to leave the secant squared of x's in there just to show the process of actually canceling. As you can see, we have secant squared of x's in both terms. We can effectively factor that out to be a factor of secant squared of x out in front. Cancel both of these. That effectively cancels these, and all you would be left with is u to the fourth plus u squared du, and it's an indefinite integral, so no bounds. This becomes a power function, u5 over 5 plus u3 over 3 plus c. We plug in tangent for u, we get tangent to the fifth, x over 5, that's a 5, not a 3, my bad, 5 plus tangent cubed of x over 3, and then plus c. Is there any solution that matches our answer here? That would in fact be choice C. Hello everybody, thank you for joining me today. We're going to go over question 6. Compute the integral from 0 to pi over 3 of tangent cubed of x secant x dx. For right now, I'm leaving out the bounds because I don't want to have to keep writing them over and over again as I solve this integral, but we'll incorporate them at the very, very end. With that being said, like in problem 5, we have an exponent greater than 2 attached to one of our trigonometric functions. This is almost never a good sign, and we always want to try to reduce it to be product of terms with exponents of less than or equal to 2. In this case, we can split this up into tangent squared of x times tangent of x times secant of x, and as you may already be able to see, a u substitution begins to emerge. Now, it doesn't quite happen just yet because we would need some function of secant x out in front, but that is pretty easy to get thanks to a nice clever identity that states that the tangent squared of x plus 1 is equal to the secant squared of x. Move 1 over to the other side, isolate tangent squared of x, you get secant squared of x minus 1 is equal to tangent squared of x. We can use this trigonometric identity to our advantage in this problem. This becomes secant squared of x minus 1 multiplied by tangent of x, secant x, and then dx. Distribute secant squared of x, tangent of x. Actually, in fact, I'm going to flip this around to better visualize the u sub that we're about to mog, or what we're about to do to mog on this nice function here, and then minus secant of x, tan of x, dx, and ba-boom, look at this. Secant of x, tan of x integral becomes secant of x at the according bounds, and this becomes a nice u sub. u in this case would be equal to secant of x du dx becomes sec x tan x. And then from there, we isolate dx to be on its own and to be in terms of du and secant of x and tan of x. That would become dx is equal to du over cx tan x, like so. Now, we can plug this back in. We get u squared multiplied by secant of x tan of x multiplied by du over secant of x tan of x. This all cancels like that. Now we're left with just from 0 to pi over 3 of u wrong. I was wrong. It would instead be secant of pi over 3 over 3 and secant of 0. Why is it the case now? Well, that's the case because we've changed bases from x to u, so now our bounds need to be, instead of being in x, need to be in terms of u as a function of x. So this is synonymous with saying that secant of pi over 3 is actually equal to u of pi over 3, and secant of 0 is equal to u of 0. Secant of pi over 3 would just become 1 over 1/2 is equal to 2. U of 0 is equal to 1 over cosine of 0. As we know, cosine of 0 is equal to 1. And there are our bounds of integration. So it's the integral from 1 to 2 of du squared du. And we're going to bring this bad boy back down from the grave, or back up from its grave. So our full integral becomes u cubed over 3 integrated from 2 to 1, and then minus this part of the function here, secant of x from 0 to pi over 3. This becomes 8 over 3 minus 1 over 3 minus, in brackets, secant of pi over 3 was established as 2. Secant of 0 is 1. This becomes 7/3 minus 1 is equal to 4/3. This is the solution to our parabola. Hello everybody, thank you for joining me today. I hope you're having a good day as you watch this video. We're going to go over question 7 of this problem set. Compute the following integral from 0 to 3 over root 2 of x squared over in quantity square root of 9 minus x squared dx. Okay, so let's highlight something important here. This on the bottom should immediately clue us to our approach to this problem. We have a 9 minus x squared on the bottom, and we can relate this to a trigonometric identity I hope you've already seen, that being that sine squared of x plus cosine squared of x is equal to 1. Why is this important? Well, if you move one of these over to the other side, you end up getting that 1 minus cosine squared of x is equal to sine squared of x, or 1 minus sine squared of x is equal to cosine squared of x. And you can pretty much start to see the resemblance here. Now, the only difference being that we have a 9 instead of a 1 in front of it. So intuitively, what we need to do is we need to multiply this value of sine squared of x or cosine squared of x by 9 as well. So this would in fact become 9 minus 9 cosine squared of x or sine squared of x is equal to 9 sine squared of x or 9 cosine squared of x, right? Now, I'm going to quickly make a variable change here. I'm no longer going to call these x's. I'm going to call them all thetas, just for the purposes of this problem, because our original integral is already in terms of x, and if we just have two separate bases in terms of x, well, that doesn't really make sense. So I'm going to define our trigonometric side as theta and our regular side as x, which hints at what I'm going to say next about what type of solution we're going to have here, and that is an approach via trigonometric substitution. Okay, so we pretty much have already found our x squared here. We can say that x squared must be equal to either 9 cosine squared of theta or 9 sine squared of theta. And for the purposes of this problem, I'm going to move ahead and define one. So you can use either one of them in this case. Eventually, if you get your bounds correct, no matter the solution that you use, whether it be 9 cosine squared of theta or 9 sine squared of theta, your solution will end up being the right one. So I'm going to go with 9 sine squared of theta in this case just for fun. In that case, x squared becomes equal to 9 sine squared of theta. That means that our x function here, in terms of theta, would be equal to 3 sine of theta if you take the square root of both sides. Now, why would this be important then? Well, if we're going to try to make the base change from x to theta, we also need to know how x changes with respect to theta in order to make the proper integration. If that is the case, then we do literally, as I said, we try to find how x changes with respect to theta. That would in fact be dx d theta, and finding the derivative of 3 sine theta. Obviously, that is 3 cosine theta. And now, if we want to make this proper base change, we must isolate dx to be on one side and set it in terms of theta and d theta on the other. Algebra wizardry finds that dx is equal to 3 cosine theta, d theta, and now we're ready to start setting up our new trigonometric substitution integral. But before we do that, I want to highlight then that if we're changing bases from x to theta, that also means that our bounds are changing from x to theta. These bounds are both x1 and x2. They're in terms of x. So it makes no sense for them to remain to be in terms of x if the rest of our integral is in terms of theta. The way that we do that instead is, well, we already have our function x in terms of theta. All we need to do is plug in both 0 and 3 over square root of 2 as our x values, and then solve for their corresponding theta values. So I'm going to go ahead and quickly do that. Our x1 must be correspondent to 3 sine of theta 1. x1 is equal to 0, is equal to 3 sine of theta 1. We don't even need to do math here. Theta 1 is obviously 0. And the same goes for x2, is equal to 3 sine theta, and this would be our second theta value. This would be equal to 3 over root 2 equates to sine times 3 of theta 2. Cancel out the 3's. You are left with 2 root 2, or actually, better yet, I'll write it like this. 1 over root 2 is equal to sine of theta 2. This may look like an unrecognizable form, but this is really just root 2 over 2 if you multiply both sides of this fraction by root 2. So root 2 is equal to sine of theta 2. This is also pretty obvious using the unit circle, that theta 2 in this case would be equal to pi over 4. And then we have found our two bounds. Great. So these would be our two bounds here. Theta 1 is equal to 0, and theta 2 is equal to pi over 4. With that, we're ready to set up our integral. The integral would be from 0 to pi over 4, as specified a second ago, of... Now we take this x, and we replace it with 3 sine theta. So 3 sine theta squared, and then square root of 9 minus 3 sine theta squared, and then 3 cosine theta d theta. I've pretty much automatically just swapped dx for its equivalent value of 3 cosine theta d theta, as found by this function here. This is the complete base change from our regular x values into theta coordinates. We're going to expand out the integral. 0 to pi over 4 of 9 sine squared theta over in square root 9 minus 9 sine squared theta, and then that would be multiplied by 3 cosine of theta, finally d theta. This turns into 9 cosine squared theta under the square root. That also turns into, that eventually turns into 3 cosine of theta on the denominator. If we're going to write that out, that becomes 0 to pi over 4 of 9 sine squared theta over 3 cosine theta. 3 cosine theta multiplied by 3 cosine theta d theta. Cancel these out, and we're left with our final integral form. This would become 0 to pi over 4 of 9 sine squared theta d theta. And this is where we'll use something that is called the power reduction formula, that essentially says that sine squared of theta, or cosine squared of theta can be equal to this function, 1 plus or minus cosine of 2 theta over 2. Now, I don't know the intuition or the derivation behind this, but you'll have to trust me. It is a very important formula that you'll need for many of the classes here at Purdue for math. I'd keep this in mind. So, if it's sine squared of theta, it's minus. But if it's cosine squared of theta, it's plus. So let us use this identity as needed for this integral. If we do that, we would obviously use the minus version. That would become 9 times 1 minus cosine of 2 theta over 2, and then d theta. You can bring out a 9/2 as a constant to simplify the integral. 1 minus cosine squared, 1 minus cosine of 2 theta d theta, again from 0 to pi over 4. When you integrate that, that's pretty simple. That's 9/2 multiplied by theta minus sine 2 theta, all of that over 2, and then from 0 to pi over 4 as the difference. I will highlight this to be in red and this to be in blue. We're going to write this out. This is 9/2 multiplied by pi over 4, substituting our theta, minus sine of pi over 2, and then minus, okay, I did not write that in red at all, so that's pretty much useless. Just imagine that I wrote it in red as the first evaluation. And this would be 9/2 multiplied by 0 minus sine of 0 over 2. That's not theta, that's 0. I'm sorry. Theta here, that becomes 0. And so you'll see all of these terms equate to 0. I keep writing thetas, Jesus Christ. To 0, and then this one equates to 9/2 multiplied by pi over 4, and then multiplied by 1/2. Yes, 1/2. But to suit our answer choices, this can be better written as 9 over 8 multiplied by pi minus 2, and this does in fact match one of our answer choices. That would match answer choice A. Hello everybody, thanks for joining me today as we cover question 8 of this problem set. I hope you're having a good day as you watch this video. Let's get right into it. Compute the integral of dx over the square root of x squared minus 4x plus 3, and we're given 5 different answer choices. So the first thing that we should be able to see is that we have a polynomial on the denominator, and it's inside a square root. So if you can recognize this problem, you may be already able to recognize what form or what approach we'll take to solve this integral. And that will be using something called completing the square. Completing the square says that if I have a polynomial, and I'll just keep it general to this form where a in this case equal to 1, of x squared plus bx plus c, I can rewrite this polynomial to be x, or in its vertex form, of x plus b over 2 squared, and then minus some constant out in front. I'll call this constant d. Now the reason why we need to have this constant out in front is because these two should be equivalent to each other, but if we set them equal to each other and then we just expand everything, we get x squared plus bx plus b squared over 4. But as we can see, b squared over 4 on its own is not equal to c, which is why we need to actually offset that by a factor or by a constant of d. So as you can see, b squared minus 4d would be equal to c in this case. And that's the principle we're going to use today to solve this integral. And that will set up grounds for using a trigonometric substitution as we continue with this problem. So let's do that. We have here the polynomial of x squared, or actually I'll write this down below here. So the integral of dx over the square root of x squared minus 4x plus 3. We see that our b value is 2. We see that our b value is 4. And we're not going to care about this one just yet. We're going to come back to that in a little bit. But we know right now that at least one component should be x minus 2 squared. And then minus some offset afterward, right? So let's take that. We see x minus 2 squared minus d should be equal to our original form, x minus 4x plus 3. We expand this, we get x squared minus 4x plus 4 minus d is equal to x squared minus 4x plus 3. You'll notice that a lot of these do cancel. This cancels, that cancels. And we're left with this. 4 minus d is equal to 3, which means that d must be equal to 1 in this case. So, I'm actually running out of room already. All right, another diagonal line. Now we can turn our integral into this format, dx over the square root of x minus 2x, x minus 2 squared, and then minus 1. And if you're astute in your observations, you may notice that this actually represents the form of secant squared x minus 1 is equal to tangent squared of x. So we can use this trigonometric identity to solve this integral. Now the question is, how exactly do we make this transformation? Well, we can see here that this 1 is analogous to this 1, and this secant squared has to be analogous to that x minus 2 squared. In this case, we say that x minus 2 squared would be equal to secant squared of x, or in this case, I'll say secant squared of theta, and let me write that all to be theta, just because we can't have two different bases all in terms of x. That wouldn't make sense logically, right? So that means that then x minus 2, after square rooting both sides, is equal to secant of theta, and then x would be equal to secant theta plus 2. Actually, we don't even need to make this change. We just say x minus 2 is equal to secant theta. We'll leave it at that. Now, to make the basis from x into theta, we obviously need to figure out how x changes with respect to theta to make this integral or this change of basis happen. And the way that we do that is literally as it sounds. Take the derivative with respect to theta on both sides. This becomes dx d theta, and then minus d theta of 2. That just becomes 0, is equal to d theta of secant theta. Wow, I'm really running out of room here. I'll come back to this in a second. So that means this becomes 0. Dx d theta would be equal to secant theta tan theta. And now we need to isolate dx, use algebra wizardry, as my physics teacher used to say. Move this d theta over, and we're left with dx equal to secant theta tan theta, and multiplied by d theta. Okay, now for the purposes of finishing up this integral, I am going to erase the rest of this here, because we really don't need this. And in the meantime, I'm going to go on a little rant about Clash Royale, because I am close to 9K trophies. I was actually sitting at like around 8,700 for those that play Clash Royale, and every single match I was getting people that had like cards 4 levels higher than I was, and so I was just getting creamed and crushed. It was horrible. So I might consider leaving the game at some point, but nevertheless, let's continue on with this problem. Our integral from the integral of dx of x squared, x minus 2 squared minus 1, we can turn that into whatever dx is equal to on the top, which would be secant theta, tan theta, and d theta, and then over, and we recognized before that we can set x minus 2 is equal to secant theta, so this becomes secant theta, or secant squared theta, minus 1. That is equal to tan squared of theta. Under the square root, that becomes tan theta. So we have here integral of secant theta tan theta over the square root of tangent squared theta, which we just said before is equal to tangent of theta d theta. Our tangents will cancel out, as I just went on a tangent, and all we're left with is the integral of secant of theta d theta. Now, this is where things start to get a little bit tricky, because it looks like we don't know how to integrate secant theta, but there is one clever trick that we must use here. I'm going to bring the integral out to the middle of the page here, integral of secant theta d theta, In this case, what you need to do is you need to multiply both the numerator, which is secant theta, and the denominator by secant theta plus tan theta. And as you may notice that we haven't really changed the integral at all. We can pretty much cancel out both the numerator and the denominator here, but doing this allows us to perform a u substitution, and you'll see in a second. We're going to distribute secant squared of theta plus secant theta tan theta is equal to, and I'm going to flip this around, this would be tan theta plus secant theta, d theta. Now our u sub becomes apparent. U in this case equal to denominator, tan theta plus secant theta. Du d theta is equal to secant squared theta plus secant theta tan theta, which is conveniently our numerator. So we make the basis change from d theta into u. This integral becomes secant squared theta plus secant theta tan theta du, and then multiplied by u multiplied by secant squared theta plus secant theta. Oh my gosh, my handwriting is not in today. Secant squared theta plus secant theta tan theta. These both cancel out, and all we're left with is the integral of 1 over u du, which is obviously just the natural log of u, but now we have to sub in what u is equal to. So u, in this case, is equal to, u would be equal here to, okay, hang on, let me write this out actually. So this would be ln of u, which is equal to tan theta plus secant theta. So I'm going to write secant theta plus tan theta. And we already know what secant theta is. Secant theta is x minus 2, but then what is tan theta, and how can we relate tan theta to secant squared of theta? Or how can we relate tan theta to secant theta? Okay, well, we use this trigonometric identity here. Secant squared of theta minus 1 is equal to tan squared of theta. That would just be the square root of secant squared of theta minus 1 is equal to tan theta. We know what secant squared of theta is. That would be this x minus 2 quantity squared minus 1, that would be equal to tan theta. And now our full solution emerges. Ln of, what is this? X minus 2, and then plus the square root of x minus 2 squared minus 1. And then plus c out in front. Now, you may not see this in the answer choices, but this is if you just distribute it out, you expand it out fully, this would become x squared minus 4x plus 3. And as you may see, this does in fact match answer choice E. Hello everybody, thank you for joining me today as we cover question 9 of this problem set. I hope you're having a good day as you watch this video, and if you hear a little something different with my voice, that is because I have fallen sick. I'll just share with you all today that this is the first day, or the first time that I've ever went ice skating, and I had a blast actually. I mean, I fell a crap ton of times and I probably broke my tailbone. Super fun anyway. But let's dive in. The proper form of the partial fractional decomposition of the rational function and this blob here is, and then 5 more blobs. So first, let's just go over what partial fractional decomposition is. That's to say that if I have some equation here, 1 over x plus 1 over x minus 4 is equal to 2, as an example, well, it's hard to work with just these two, the sum of these two rational functions here, but one thing that we can do is turn it into a fraction with a common denominator. And to do that, we would multiply the first term by x over 4 minus x over 4, or x minus 4 over x minus 4, and this side by x over x. Effectively, we're not really changing anything about this equation here, but we're just making it possible to combine this into a common denominator, or a fraction with a common denominator that would look like that, right? And partial fraction decomposition just says that I can take this blob here and turn it back into its components. Now, there are a few rules that we need to cover in order to fully understand partial fractional decomposition. The first one is that if I have some function f of x on the top, and then I have some function x to the n plus dot dot dot, in this example, I'll use something like x squared plus 2 over x cubed plus 2x plus 4, if the bottom is unfactorable or irreducible to the product of terms with lower degrees, then our general solution on the top has to be the general equation or the general form of the function that is 1 degree less than that of the bottom. So in this case, that would be ax squared plus bx plus c, or the function of a polynomial, because our bottom one here has a principal irreducible degree of 3. And the reason we need to do this is just to consider pretty much all possible scenarios, because in this example that we have seen on the left, you can't factor this down, so all we're left with as a possibility is some x squared plus something 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 over x cubed plus something something something, and as you can see, that same form is represented in this general format. Now, the second rule that we need to keep in mind is if I can take any function u of x, we'll say u of x in this case is equal to x squared plus 4, and then I can rewrite my polynomial fraction to be of form u of x to some power of n, then the full fractional decomposition of this function would look as follows, and I'll explain why in just a moment. This would be ax plus b over x squared plus 4 to the n plus cx plus d over x squared to plus 4 times n minus 1 plus so on and so forth. And the reason why we can do this is our general solution at the top only has to have the degree of 1 less than whatever, like the highest degree of whatever is inside of that parentheses exponent sort of unit. So in this case, our highest degree in the denominator that we care about is x squared, which means that our top must have a form of ax plus b, or a line, which is a degree 1 less than a polynomial. Or not a polynomial, but a quadratic function is what I mean to say. And the reason we need to think of it like this, where we need to start at the nth degree and then work our way down to n minus 1, then n minus 2, then n minus 3, all the way down until something like maybe k, hij, kx plus l over x squared plus 4 to the 1 power. The reason why I need to do that, and that can be pretty easily found, or that can be pretty easily represented. Let's say that I have an example of x squared plus x plus 4, and that that's all over x cubed. I can rewrite that as the sum of its individual split terms. So this would be x squared over x cubed plus x over x cubed, and then plus 4 over x cubed. And that would turn into 1 over x plus 1 over x squared plus 4 over x cubed. And as you can see, our deconstruction of this function contains every degree on the new denominator from 3 and 2 until 1. So we need to follow the same format as before, just to account for every possible condition or every possible scenario, so we're not leaving behind any potential solutions to our decomposition. Now, with that being said, we can take what we've applied and then begin solving this problem and looking for the correct answer. So let's take this function and we're going to decompose it. The first thing that we want to work on is this x squared out here. So we can actually approach each of these products or each of these factors in the bottom individually, and then we can sum pretty much all of their decompositions together to create one giant equation or one giant expression. So if we have x squared on the bottom, in this case, our u function that sits inside of the exponent is just x, which means that our general solution on the numerator should just be some constant value, because that is 1 degree less than the polynomial degree on the bottom, which is 1. So, as before, we need to include every term from x squared all the way to x to the 1th, or x to the 1st. That would just be this, right? So this one is complete. We can cross that off. Now let's consider this one, x squared plus 4. We know that x squared plus 4 cannot be factored any further, just because if you factor it any further, you would begin introducing imaginary numbers, and we cannot have that for a problem like this. In which case, our highest degree of general solution should be a degree of 1, which is the general format of a line. The general format of a line, let me remind you, would be y equals ax plus b, and we're looking for this right here, the general form. So a and b are already taken up, which means that we now have to use c and d. So cx plus d as our general solution of 1 degree lower than the denominator, and the denominator being x squared plus 4. And we have nothing else to care about, so we can cross this one off the list too. And finally, all I have to care about is the x squared plus 2x plus 5. And like the x squared plus 4, this is also irreducible or unfactorable. And we also notice that the highest degree in the x squared plus 2x plus 5 quadratic function is a degree of 2, which means that this general solution must also be that of a simple straight line, which is again a form ax plus b. A, B, C, D are all taken, so all left to do is ex plus f, and then over x squared plus 2x plus 5. And then that would be represented by solution B in this case. So just to summarize, we covered partial fractional decomposition, and then the two rules that you must follow. Your general solution to a denominator term should be the general format of the expression or the polynomial function that is 1 degree less than the denominator. So in this case, it's ax squared plus bx plus c, because the largest degree on the bottom is x cubed, or the largest degree of the irreducible fraction on the bottom is x cubed. And then let's say that you can represent this giant function of x cubed plus 2x plus 4 as some function u of x. If u of x is raised to some nth power, then you need to include all possible solutions from when the denominator is raised to the power of n to when it's raised to the power of n minus 1, and then all the way down to when it's raised to the power of 1. And we show that below by taking this example as our sort of demonstration of this rule. So to summarize, solution B would be our answer following the work that we just did. Hello everybody, thank you for joining me today as we cover question 10 of this problem set. Compute the integral from 4 to 5 of 12 over x squared minus 2x minus 3 dx. So we can see here right off the bat that this polynomial at the bottom can be factored into x minus 3 multiplied by x plus 1, in which case we can use partial fractional decomposition. Partial fractional decomposition is just to say that if I have this combined thing here, I can reconstruct it as the sum of some constant over x minus 3 plus some other constant over x plus 1. So this should all be equal to that right there. So let's set them equal to each other, and we're going to solve for the constants of a and b. x minus 3 times x plus 1 is equal to a over x minus 3 plus b over x plus 1. And the reason why we can do that is we can think about it in the reverse. Let's say that, for example, that I have some function like 1 over x plus 2 plus 1 over x minus 2, and I'm trying to solve for x if all of that is equal to 2. Well, obviously we don't want to keep it separate. We'd want to combine the function into a fraction with a common denominator. And we would do that, multiply everything up here by x minus 2 on the top and bottom, plus x plus 2 over x plus 2, x minus 2, and that would be all equal to 2. That would be 2x over x plus 2 to multiply by x minus 2. And you can see we've taken the sum of two of these terms here, and we've combined it to be this. Partial fractional decomposition just says that I can take this giant function and turn it back into the sum of these two terms, which is exactly what we're going to do here. But because we cannot guarantee that the coefficients on the top are going to be 1, we have to leave them as arbitrary constants a and b, or arbitrary variables which you have to solve for. So with that being said, we're going to do this algebraically. We do 12, we're going to multiply everything here by x minus 3 times x plus 1, just to get rid of these ugly denominators on the bottom. That become 12 would be equal to a times x plus 1 plus b times x minus 3. Now the way we do this is we can say, okay, well, I can get rid of a or I can get rid of b if I plug in the right values of x. So if I plug in -1 for a becomes 0, but then b becomes multiplied with -1 minus 3. That would be -4b is equal to 12. Now you can see that b is equal to -3 if we plug in x equals 1, x equals -1. And we can do the same thing for a. If we do 12 is equal to a and then 3 plus 1, because we're going to plug in 3 to cancel out the b term here, that becomes plus b multiplied by 0. 12 is equal to a times 4. We can see that a is equal to -3. And then from there, we can begin solving our integral. So I'm going to, well, I don't want to erase that just yet. So I'm going to rewrite the integral here from 4 to 5 of 3, and keep this in mind. Originally, 3a equals 3 goes with the term of over x minus 3, and b is equal to -3 goes with the term of over x plus 1. As you can see from our original decomposition here, or our original deconstruction. So we're going to do that again. 3 over x minus 3 plus, minus 3 over x plus 3, not x plus 3, that'd be x plus 1. X plus 1 dx, and this just becomes the integral of two rational functions of form 1 over x minus something, which would just become the natural logs of both. So this becomes 3 times ln of x minus 3, and this becomes minus 3 times natural log. Why am I writing LLM? Freaking ChatGPT's all over my mind right now. ln of x plus 1 from 4 to 5. This would become, if we just do the differences here, that would be 3 ln 5 minus 3 minus 3 ln 5 plus 1, and then minus 3 ln 4 minus 3 plus minus, put this in the brackets actually, 3 ln of 4 minus 3 plus, I keep writing minus 3 ln of 4 plus 1. So this becomes 3 ln of 2 minus 3 ln of 6. This becomes minus 3 ln of 1, and then plus 3 ln of 5. So as we know, 3 ln of 1 becomes 0, so that term is gone. When you have the subtraction of two different natural logs, this would become ln of 2 over 6, and then finally plus 3 times ln of 5. When you have the addition of two natural logs, that becomes 3 times ln of 2 times 5 over 6, and then that would be our solution here. So that would be 3 times ln of 10 over 6, which is equal to 3 ln of 5/3. Does that match an answer choice? That would be choice A. Welcome and welcome back, everybody. Thanks for joining me today as we cover question 11 of this problem set. Compute the integral of 1 to 3 of x squared minus 1 over x cubed plus x dx. Now this one, for me, I'll admit, was actually a doozy. This one was pretty hard. But the first thing we can do is we can factor out an x from the denominator. That should become this dx, and then from there we have the product of multiple fractions, or the product of multiple polynomials in the denominator. That should be screaming to us, okay, how about we use partial fraction decomposition for this problem? I have a whole explanation of how partial fraction decomposition works in question 9. I'm not going to re-reference everything here, just because that's redundant. So if you really need help understanding what PFD is, please reference question 9 explanation, please. Thank you. Now, x squared minus 1 over x times x squared plus 1, we can deconstruct that into some form. A over x plus bx plus c over x squared plus 1. From there, I'm going to multiply everything out by x times x squared plus 1. This will eliminate all the fractions and leave us with nice numerators on top, and only that. So a x squared plus 1 plus bx plus c multiplied by x. All right. So right off the bat, we can solve for a if we just plug in 0. Because if we plug in 0, b and c immediately become eliminated. So let's do that. We plug in 0, this becomes 0 minus 1 is equal to a multiplied by 0 plus 1 plus, and then 0 here. We can clearly see that a would be equal to negative 1. Now, we can plug a back into the equation and then solve for b and c. We have x squared minus 1 is equal to negative 1 multiplied by x squared plus 1, and then I'm going to distribute bx plus c out. This becomes bx squared plus cx. And it may not jump out to you at first, but you should notice that these polynomials have to be equal. This polynomial has no presence of any term dx or kx, any term of a constant multiplied by x to the first power. However, this side with a general solution does. What does that tell us then? That tells us that cx in this case must be equal to 0, in which case c also should be equal to 0. We can guarantee that c must be equal to 0 in this case because no other term in this side, the right side of the general solution, or the right side of this equation, can be distributed to form some term kx. So we know that c in this case is already equal to 0. That just leaves us to solve for b. So now we're just left with x squared minus 1 is equal to negative 1 multiplied by x squared plus 1, and then plus bx squared. We need to figure out how to arrange this side to become equal to some constant, b plus something. Actually, I didn't write that out. But we need to figure out how to rearrange this to be a form of this, where it's x squared minus k, or something like that. So the way we're going to do that is we're going to distribute out this part right here. This becomes negative x squared minus 1 plus bx squared is equal to x squared minus 1. This becomes b minus 1 x squared would be equal to x squared minus 1. Oh, and then minus 1 here. And as you can see, these equations are pretty equal to each other, or they look pretty similar. We have some x squared term here, and then we have some x squared term here. The only difference, and then we also have the negative 1 out here and the negative 1 out here. Now the only difference with these equations is that the coefficient of the x squared term is equal to 1, but not here. It's equal to b minus 1. So we have to solve for b such that b minus 1 would be equal to 1. In this case, b should be equal to 2. So if we plug the b back into this equation, we'll see that these equations become equal. This is 2 minus 1. X squared minus 1 is equal to 2 minus 1 multiplied by x squared minus 1. This turns into x squared minus 1 is equal to x squared minus 1 at the very end. All right. Now from there, we have found all of our constant values. A is equal to negative 1. B is equal to 2. C is equal to 0. And we can finally construct the integral. So we have from 1 to 3 of, what is this? So it's a over x, that'd be negative 1 over x, and then plus bx plus c. We know that b is equal to 2, so it'd be 2x, and then plus 0, so just 2x on the top, over x squared plus 1 dx. We can split this up into two integrals. One of them is just the natural log. The other one becomes a u sub. So I'm going to focus on the u sub 1, but the u sub 1 is actually really, really clean, which is super nice. This becomes the integral from 1 to 3 of negative 1 over x dx, and then plus the integral from 1 to 3 of 2x over x squared plus 1, and then dx. So this one turns into negative ln of x from 1 to 3, and then plus this one becomes a u sub. U in this case would be equal to x squared plus 1. Du dx would be equal to 2x, and then from there you can flip everything around. Dx over du is equal to 1 over 2x, and then you can finally solve for what dx should be in terms of 2x and du. Dx is equal to du over 2x. The reason why we need to know what du is, why we need to know what dx is because, as you may know, we're simply just going to sub this in and make the final change of basis as we've been planning to with the u substitution. We can finally do that, but before we do, we need to figure out what the bounds are. And the bounds in this case, they are already to be in terms of x. This would be x1, this would be x2, but the minute we make the substitution or the change of basis into basis of u, we need to figure out how the bounds can be represented as u instead of as x. And that's pretty simple. We already know how to relate u to x. U here is equal to x squared plus 1. All we need to do now is just plug in our x bounds into the u function and then solve for u. So the first one, we'll say this is the lower bound, will be equal to 1 squared plus 1. We know that u1 should be equal to 2. And then u2 would be equal to 3 squared plus 1. We know that u2 would be equal to 10, right? So then our bounds becomes clear. This is from the integral from 2 to 10 of 2x over u multiplied by du over 2x. These eliminate. Now you're left with negative ln of 3 plus ln of 1, and then minus the integral here of 10. Not the integral, but you can rewrite this as du over u. So it'd be the integral from 2 to 10 of du over u. That would simply become ln of u from 2 to 10. I'm going to put that on parentheses. We know that ln of 1 is equal to 0, and we just leave ln of 3 as it is right now. So it becomes negative ln of 3 minus, in parentheses, ln of 10 plus, ln of 10 minus ln of 2. Okay, so we can rewrite this to be negative ln of 3. Oh, sorry. Before we do that, I'm actually going to move to the next page quickly. So this would become negative ln of 3 and then minus ln of 10 plus ln of 2. We can rewrite this to become ln of 2 minus ln of 3 minus ln of 10 to make it a little bit easier to understand. From there, this becomes ln of 2 over 30th. That's not correct. Oh, sorry. Plus ln of u. Yes, that'd be plus. Then this would become plus. That would become minus. Plus and then minus. Okay, gotcha. So then this would become ln of 10 minus ln of 3 minus ln of 2. This becomes ln of 10 over 6 because logarithmic properties allow for subtraction of logarithmic functions to be the division of their terms, which would become ln of 5/3. That would be answer choice D. Welcome and welcome back, everybody. Thank you for joining me today. We're going to go over question 12 of this problem set. Evaluate the integral from 0 to infinity of x times e to the negative x squared dx. This may look like integration by parts to you, but notice that we have an x squared in the exponent and an x out in front. This should instead be screaming to us u substitution. So in this case, our u will be negative x squared, our du dx, because we're going to change from basis of u from x into u. So we need to figure out how u changes with respect to x. So du dx becomes negative 2x. Algebra rules of we flip this over. Dx du is equal to 1 over negative 2x, and then dx would be equal to du over 2x. All right? And then from there, we do 0 to infinity of x times e to the u du over negative 2x. So that cancels. We're left with negative 1/2 out in front multiplied by 0 to infinity. However, our bounds now change actually because we have changed basis. So we need to be able to find these bounds, which are in terms of x, to be in terms of u instead. And that's pretty simple. We just need to plug in x here, and we need to solve for u. So u of 0 would be equal to negative 0, which is 0. U of infinity would be equal to negative infinity. Yeah, just negative infinity. I mean squared, but that's still just negative infinity. So negative infinity here. Okay, e to the u du. This is a very simple integral. This would become negative 1/2 out in front multiplied by e to the u from negative infinity to 0. So that would be 1/2 multiplied by e to the negative infinity, or actually, okay. I just realized I missed a very important component in here, and that is that this is actually an improper integral. So if that's the case, then our limits here, our limit of infinity here, we can't have infinity as one of our bounds because infinity can't be a bound. It's literally unbounded. So we need to represent this as a limit instead. So we can represent this value of infinity to be instead a value represented by some variable b, and we can say the limit as b approaches infinity of this integral whose bound is b. And in this case, it would be the same thing here, or it would be negative b squared. The limit as b approaches infinity yet again. And so we bring out the limit again from here. I completely forgot about that. But I mean, you could go on about the integral without even thinking about that, regardless. But just to remain faithful to the nature of the improper integral, we're going to include the limit here. So this would be the limit again as b approaches infinity of negative 1/2 of e to the u of 0 to negative b squared. This would turn into negative 1/2 multiplied by e to the negative b squared, and then plus 1/2 e to the 0. And then again with the limit. So limit as b approaches infinity of negative 1/2 over 1 over e to the b squared as b approaches infinity plus 1 over e to the 0. As we can see, this term is going to approach 0 because e to the b squared approaches infinity, so 1 over e to the b squared should approach 0. This term all goes to 0, but this term remains as 1/2. So this is the solution to our integral. Our solution should be